So you're more than welcome to come further up if you want to. I know this is kind of the last day and people are probably pretty tired. So quick background, my name is Harshil. I'm the founder and CEO of Dendrite. I have a background in pure math, mechanical engineering. I've been in this industry for about 5 years now, just trying to learn and figure things out. The point of this talk is to talk about materials and process development in either jetting and photopolymers, and honestly just educate people about what that's all about and give them links, because I think a number of folks in this industry are woefully miseducated or just unaware of what type of information is out there. So kind of as a show of hands, what are you interested in learning about? Like, is it more on the jetting side, the photopolymer side? So raise your hand if you're interested in jetting stuff. Okay. Well, the jetting people are clearly the guy who sells print heads is probably interested. Okay, and I'm guessing that are the rest of you potentially interested in photopolymers or photopolymerization? I'm guessing. Okay. Well, I'd say feel free to interrupt and ask questions if you have anything. Just raise your hand and I'll interrupt and stop. So what is Dendrite? So Dendrite's mission is to fundamentally change how geometry is created, transformed, and transmitted on a computer. So what does that mean? It means that you want to be able to take an idea and design it. You want to take an already idea that's been designed as either mesh data, CAD data, etc., and transform it, for example, slice it. And then you want to be able to transmit it in an efficient way to the machine so that it doesn't take forever to transmit all that data to the machine, right? So that's kind of what we do as context. And so what's the goal of this talk? It's to talk about what is materials and process development from a jetting context, and ultimately this understanding is meant to expand the envelope of what's possible, right? What types of machines can be built, what types of parts can be built, what types of materials are available, all that good stuff. And so, I'll repeat myself a little bit here, but a number of people are looking at more multi-material types of machines. If you see a number of OEMs here, they're trying to stack print heads or stack substrate and powder and do all kinds of interesting stuff. If you've gone to any of the talks here and asked a question about, well, how does that work? The usual answer is, well, it depends on the geometry. And that's true, right? Depending on what you're trying to print or make, different things start to affect the process, because the processes that we're dealing with, regardless of whether it's laser powder bed fusion, jetting, or photopolymerization, they're all so intricate that we're trying to really push the limit of the physics of the process now. More importantly, once we have these new materials and parts dialed in, you want to make sure that the process is repeatable, traceable, and you want to be able to qualify it and make sure that the parts that you're producing are of quality, right? Primarily, they have the right material homogeneity, material properties, all that good stuff, right? And then of course, kind of as like an extra plus one, if there's a way to minimize the supports in your process or improve the manufacturing process by doing some kind of compensation, you want to go do that, right? So for example, a number of people are trying to not print supports in laser powder bed fusion, for example. So as I mentioned, right, the current state of affairs is kind of a lack of education, and I by no means actually know much in this field. I've just been interviewing people. Like, full disclosure, I interviewed Dan here. He's probably forgotten more than I've ever learned in my life about the subject, right? And so my goal was to take that information and try to kind of give a survey of what's what, and then provide links to where you can learn more about it, right? Ultimately, I think this industry is going to get a lot better once the education around what's happening, why it's happening, kind of improves. So, kind of what are the key challenges when we're talking about a jetting machine? Well, of course, there's making the machine itself, right? There's all kinds of physics and interesting things going on there. There's the actual jetting process itself, because print heads are very complicated electromechanical things that have microfluidics and all acoustic aspects all across the board. There's the material itself, because when people try to make a jetting machine, usually that person is a material scientist or a chemist, not a mechanical engineer, right? So they're trying to make some kind of new substrate, some kind of new powder, or some kind of new binder. And then ultimately, the biggest challenge, which Dendrite has a part in, is actually understanding how the geometry plays into all of this and providing tools to properly account for what where the geometry takes you. So kind of starting this survey, right, this slide is kind of about what are the different kinds of things that cause variations in droplet volume. And I can already see Gareth looking at me going, okay, well, the czar had fixed some of these things, and they're only in the other people that we hate or don't like because, you know, you're British and you won't ever say something like that. But it's all fine. But, you know, if I'm looking at a survey of all the printhead, you know, jetting type technologies, right, there are a number of reasons for droplet volume variation, and of course, because you're jetting something, that's kind of really important. So the most fascinating one that I kind of thought of, that Dan actually brought up to me, was the major difference between 2D printing and 3D printing, right? In a 2D printing environment, you're moving the paper or the substrate past the head, right? That's the thing you know, the physics is happening, right? Versus in 3D printing, you're moving the head past the substrate, and there is an inherent physics associated with that, right? There's dynamic pressure, there's all kinds of stuff going on, right? And that does have an effect, right? That acceleration does matter, right? And I'm mentioning this specifically because speed of the print is becoming an ever more important thing that everyone wants to talk about. And of course, the faster we move the head, the more this problem starts to become, you know, a major issue. The next part is crosstalk between the nozzles, right? So this comes in a variety of manners. So we have, you know, if we have multiple nozzles firing next to each other, right, there can be potential issues. Again, there are various head manufacturers who have come up with ways to minimize these things or remove them altogether, right? But inherently, this is an acoustic system. There is vibrations, you know, the fluid, you know, is push and pressure waves across the whole board. And all these things come together to potentially vary the droplet volume, right? And when I say droplet volume, we're talking in picoliters, right? So very, very small amounts. The next part is just due to the inherent nature of the printhead. So if you don't know, printhead works by, you know, with a piezo oscillating, right? And it basically spits out or jets out a small bit, right? Frequency is sent to the piezo, it, you know, oscillates, and then something comes out, right? And the minute that we start talking about frequencies, we're now in the realm of hardcore acoustics, right? There's things called resonance, right? And certain physical aspects of the printhead just don't want to work, right? Like, so as with all things in engineering and when we're dealing with resonance, you don't want to hit a resonance mode and what frequency you're sending to the head. You don't want to have too many frequencies because the head doesn't like major jumps between those things, right? I mean, this is a physical aspect and all these things have to kind of be accounted for. Continuing, now we can kind of get into some of the part density issues, right? There are a number of reasons why there might be part density issues. One is just due to the binder penetration, you know, into the substrate, right? At a minimum, you know, it takes time to come down, right? The amount of penetration might be different depending on the volume, and you might actually want a different amount of penetration depending on whether you're in the core of the part or on towards the edges. The other issue related to this is inherently when you eject a droplet of something and it hits a powder, there's a potential ballistic effect. Basically, the droplet might hit the powder and the powder might go somewhere else, right? You have to account for that. And then finally, there is this concept of binder bleed. So most people, including myself, until I learned more about this, you know, thought about bleed in the 2D direction, right? Because you make a droplet and then it kind of bleeds out. And then you want to that really matters on the edges when you potentially have detailing agents or things like that, because you don't want it to bleed out too much out of the part or into the part. Well, due to a capillary effect, things also bleed down inherently. This is kind of like a overcure, undercure in a photopolymer world, right? Because this is a purely physical process. And so you also want to make sure that there's enough droplet coming out so that it penetrates, but you want to make sure that there's not too much that it bleeds, and you want to make sure that it bleeds in the right direction, but not too much as well. Right, so as you can tell, this is becoming a very complicated problem that you need to kind of account for, and it's all kind of controlled by the process, the material being jetted, and the actual head itself. Kind of rounding this out, I've started seeing some other kind of higher order problems that are not necessarily directly related to the actual jetting process, but are kind of right next to it. Right, a number of people are interested in, you know, improving the green part strength. So when you take out the green part from the machine, it might need to cure and then needs to go into a sintering machine. You know, if we want to depowder this thing, you know, the stronger the green part strength, the easier it is to depowder and make sure that we have something awesome coming out. Of course, we also don't want to put too much binder into anything, because anything you put into there needs to be burned out at some point, right? So you want to optimize for that. And then finally, the holy grail of everything that's going on, right, is the shrinkage issues, right? Because inevitably when you heat something up and burn something out, something is going to shrink, right? And depending on the geometry, it's probably going to shrink anisotropically due to a variety of reasons, right? So I know that was a lot, right? Almost every single one of those things you could probably spend a decade trying to figure out. But from my perspective, from the software perspective, for me, it's the key comes down to controlling the droplet volume and location based on the physical limitations of the print head, the binder, the powder, the print speed, and the geometry being printed. That's what it basically comes down to. Before I keep going, any questions? Feel free to raise your hand. Nope? Okay. So I'm going to pump past all the photopolymer stuff and kind of jump to what are we going to do to account for all these things and what's the solution to this, right? So at the end of the day, taking a step back, the goal is to make better parts, right? Whatever that might mean. It might be make the parts faster, it might mean better material properties or surface finish or whatever, right? And the key is we want to apply compensations to this inherently physical process to make sure that we can get as close to, or if not perfect, what we decided we wanted to print. These compensations take place in the form of basically just changing colors on images. So all of these types of processes, whether it be photopolymer or jetting, they basically take an image as an input. And the image basically corresponds to where the droplets are coming, right? So if it was a monochrome image, black could mean this is where you put a droplet on, and white could mean off, don't put a droplet here. But if we went one extra step, we could add like a grayscale, for example, which would control how much of a droplet you're putting down, how many picoliters, or in the case of a photopolymer, what the light intensity is. So again, going back to it, we want to control how much you're putting down and where you're putting it down, and the mechanism to do that is essentially a colored image. So where do we want to apply these compensations? So at the end of the day, there's the hardware itself. Like as you're building this machine, there are going to be all kinds of inherent things associated with how you built the machine, what print heads you use, what drive electronics you used, all that jazz. And you'll have to apply compensations at that level. Then there's another level of what material you're using in this process, and depending on the viscosity, the surface tension, the wetting angle of the powder, all this stuff comes into effect when you want to compensate for the material. But what I'm going to actually focus on is how you compensate for the geometry. So what does geometry compensation mean? It basically means analyzing the geometry to see what is where. And what is where, like the key things that we've determined at the moment are how far inside the part you are, because are you in the core bulk, are you on the edges, how close are you to the edge, are you near like a fin which has small things on either side. And the other thing that we care about is what's the angle of the nearest surface in some way, shape, or form. Is it facing downwards? Is it facing upwards? Is it just flat? Right? All of these things, are key important aspects of where we want to potentially do something different. Of course, we could generate more kinds of geometric queries, but for the sake of simplicity, we're starting with just how far in you are and where the angle of the nearest surface is. And then the idea is you want to be able to find all those regions of interest or volumetric segments and then apply potentially either a different droplet pattern or a different strategy depending on where you are, right? But you don't want to put too many things because of course there are limitations to the head, but you do want to account for them in some way, shape, or form. So one of the things that we've developed is this voxelization system. So we can take a piece of geometry and discretize it at a very, very high resolution, usually either at the resolution of the machine or even super sampled beyond that. And we can basically find how far we are inside a part and the angle of the nearest surface. Right, so here's an example of us taking a propeller blade and basically color coding everything based on the distance to the nearest surface, and that's signed. Another example would be something like this. So this is a part made out of UTEP, and basically all the red surfaces are inward facing, the blue surfaces are upward facing, and the green surfaces are downward facing. And when we look at like a specific section, what you're actually realizing is there are actually multiple colors of red, green, and blue, and we want to potentially apply different material parameters to each of those different sections. So I don't know how easy it is to see it on here, but On the thin fins, there's basically only one red color, but on the thicker fins on the bottom, there are multiple red colors. And so you're kind of seeing the difference between a core and like the outside shell. We're also seeing like a complex lattice structure, which has downward and upward facing surfaces, and you might want to treat them differently. Again, the point is not that you're going to use every bit of information here, but the key is you might want to use this information in a sophisticated way to influence some downstream process. And as I mentioned, you can apply different grayscales. The grayscales could be applied to the core, the shell. Maybe you want to treat the lattice structures in a slightly different way. Right? All of these things can kind of come into effect. You also might want to anisotropically compensate all of these things as well. So just to kind of round this out, here's an example of a flute channel. And it's very subtle, but you can basically anisotropically compensate each of these images in such a way so that we're accounting for some of these effects. So this was a very quick run through of a lot of this. I mean, it's honestly impossible to talk about this a bunch. There's more information on our website, and I would have told you to come to our booth to get a demo, but we're kind of at the end of the road here. Hopefully this was helpful or interesting. I'm more than happy to answer questions. I also want to mention that Gareth and Dan are in the audience. Gareth is with Czar. He helped me quite a bit with some of this information. Of course, Czar sells print heads. Print heads can be used for a variety of applications in both 3D, 2D, photovoltaics, and beyond. And those Czar print heads have a number of really cool properties for high viscosity stuff. I think I did that right, Gareth. Okay, I got the keywords. And Dan, like I said, is just a host of information, has been going around consulting, and also was a major part in helping me make this presentation. So thank you, Gareth, and thank you, Dan.